All right. Good morning, everyone. Today's presentation, I'll cover some 5G basics and principles and concepts. And at the end, I'll go through some BuySells 5G products. Please don't hesitate to ask any question. This is kind of a little bit technical presentation here. We are global. We do exist in more than 55 countries, and we have 40 global partners, and we've already shipped hundreds of thousands of small cells and devices. So let's get started. So what is 5G? 5G is the fifth generation wireless systems based on 3GPP release 15 specifications. Every 10 years, there are new generation of wireless systems. 10 years ago, we had the LTE started, and most likely in 10 years, in 2030, we will have 6G. As a matter of fact, the work on 6G is already started. But now let's focus on 5G. There are three pillars when it comes for 5G. The first pillar is enhanced mobile broadband, or eMBB. The second pillar is ultra reliable and low latency communication, URLLC, and massive machine type communication, which is MTC. So if you look at this triangle right here, the first angle is the first pillar, which is the eMBB. This is about speed. So this, 5G will reach speeds more than 100 times more than faster than LTE and 10 times faster than LTE Advanced. We're going to be reaching 10 gigabits per second. And just to put this into perspective, you'll be able to download an HD movie in less than a second. Now, probably it'll take you a couple of minutes. And you can also watch 8K movies with no delays in real time. So this is some of the use cases that pertain to the eMBB. It is the UHD screens or the 8K movies. Work and play in the cloud, because sometimes currently there are some latency, but if you have kids who've been doing a lot of games on the cloud, you know what I'm talking about. Then you have augmented reality, and as we go down this side of the triangle, the ultra reliable and low latency concepts becomes more important. So it's no longer about speed and throughput. It's about latency. And latency is the delay between the sending and receiving of information. Currently, or in LTE, it's 200 milliseconds. So we'll be going down from 200 milliseconds of latency down to 1 millisecond. So some of the applications that utilize these the low latency concepts, they're self-driven cars. And what's interesting, for visual stimuluses, for humans, it'll take 250 milliseconds or a quarter of a second for you to react to any incident. When it comes to the machines or vehicle to vehicle, it'll take 1 millisecond. So that's 250 times faster than you. So imagine your car reacting to the environment 250 times faster than you. So this is just to put it into perspective too. And now, so it is industry automation and the vehicle to vehicle. That's where latency comes into play. If we go to the other side of the triangle, as you go down, we have use cases that use the smart homes, smart buildings, and the smart cities and the IoT. So MMTC, it's all about IoT. It's about density. Unlike past technology that were extremely sensitive to the number of connected devices, 5G will be able to support many devices at the same time. We're talking about 100 devices per square meter. That's the density that I'm talking about. So it's like 10 devices per square foot. And just easy to remember, it will be able to support 1 million devices in 1 square kilometer. So 1 million in 1 square kilometer, which is pretty impressive. On top of that, we have the efficiency. So this technology is expected to surpass the energy efficiency of 4G by 90%. So, and then there's another concept. It's called spectral efficiency. LTE spectral efficiency is at, what's a spectral efficiency? It's bits per second per hertz. It's in relation to the spectrum. So LTE, we used to have, or it is 5 bits per second per hertz in download, and half of that in the upload. So if we're talking about 100 megabits per second, or if we're talking about 20 megahertz of bandwidth, you do the math, 20 times 5, that'll give us the maximum throughput of 100 megabits per second. Now 5G, we're at 10 bits per second per hertz. So this is like double the efficiency of LTE, but you get much wider bandwidth. So let's take it as 100 megahertz of a bandwidth. You multiply 100 by 10, and you get 1 gigabit of bits per second as a throughput, right? Okay. There are 8 specification requirements that 5G is built upon. You can see here on this diagram, it's 10 to 100 times faster than 4G, and it's 100% coverage, 99.99 availability, over 1,000 of capacity, 90% of energy, reduction of energy, and you got battery life of 10 years for the sensors, for the IoT, massive IoT, and then you have over 100 connected devices and extremely low latency of 1 millisecond. So these 8 requirements, what actually drove 5G into reality. All right, let's talk about some characteristics of 5G. We'll start with the RAM. We have one of the terms that you will always hear, it's millimeter wave. So what's a millimeter wave? According to physics, the higher the frequency, the shorter the bandwidth. So millimeter waves, we're talking about frequencies north of 30 gigahertz, between 30 and 300. And these are the high band or frequency range to bands, frequencies according to the 3GPP specs. The advantage of the millimeter wave, since it's really high in frequency, it will pack lots of data. But the disadvantage that it is, since it's a short wave or a millimeter wave, it won't travel much and it won't penetrate. If you look at this right here, this is like a heat map for one of the millimeter wave or small cells. Let me take this away to see it. This is a radius of 100. This is a radius of 200 meters. And you can see this is the dB loss. Within 100 meter radius, the signal is great. It's very strong. Then when you go further from the cell, this is another 200, it gets weaker, but still, orange is we're in the minus 110, which is okay, but it's not as strong as minus 90. And as you go away the signal start to degrade. It start to get minus 140, minus 150. So this is just to let you know that it's extremely strong. You look at it as a hotspot, and to utilize the millimeter waves, we have small cells. 5G is about small cells because this is how you get to millimeter wave. And small cells, and you would get, the distance between each small cell and the other is like 250 meters. So they're gonna be packed. And what's good about small cells, they don't require much power, and you can always install them and they don't transmit also lots of power. You can install them on street furniture, light poles, and on top of buildings or on side of the buildings. So this will be part of the 5G ecosystem right here, small cells. Okay, another important RAN concept of 5G, it's the massive MIMO. The massive MIMO, this is, you'll have, the radios will be able to support antennas with hundreds of little antennas, of little ones. This is like an array of 100 or, even more little antennas. And what's good about this, that the capacity will be increased by at least 22 factor or more. You will have tons of antennas instead of just 2 or 4, like today's technology. So the capacity will be much improved here. Another concept is the beamforming. And instead of just broadcasting in many directions at once, the beamforming technology would actually focus the signal on the user. Not only this, it will also track the user as they move. Not just one user, track all the users as they move. So it won't waste much energy like before, just broadcasting all over the place, and it definitely would reduce interference. Okay, so these are 4 important RAN characteristics. Please, if you have any questions, just you can type it in we can answer as we go on. All right, so let's talk about the 5G spectrum. We have low band, mid band, and high band. And as I was describing earlier on, there are 2 kind of frequency ranges, FR1 and FR2. FR1 is sub 6 gigahertz, and this is used for coverage. Because that's low band, lower frequency, physics, higher bandwidth. It will travel much further than the higher frequencies. And then we have frequency range 2. It's it's at 24 gigahertz and up, all the way up to 52 gigahertz. And I just listed some of all the frequencies that have the letter N. That's new radio. That's for 5G frequencies. You can see, for instance, 260, it's at 39 gigahertz. And look at the bandwidth, 2 gigahertz. That's from 38 to 40 gigahertz. So huge bandwidth right here. And what's good, and you have, for instance, N41. What's good about 5G, there is a feature called DSS, which stands for Dynamic Spectrum Sharing. The same LTE bands also will be shared with the 5G, but they will inherit the 5G characteristics. So one way of deploying the strategy of deployment is about, this is called the wedding cake. The low band, you have, for instance, this is for 700 megahertz. This is 5G bands, okay? And this is used to cover, and this is popular land. Will have huge coverage, but it will not be as, the throughput will not be as fast as the layer on top of it. So the layer on top of it is a mid band, which is 3.5 gigahertz, which is it could be CBRS. That's kind of medium. The coverage is good, and the speed is good. But it's not as the coverage is not as good as the 700, but the capacity and speed is much better. Then we have the hotspot, which is the millimeter waves. These would be in the urbans. They'll be spread across the street furnitures, and that will deliver the speed that everybody's talking about, and the latency also. So this is called the wedding cake concept, since you will be overlaying 3 different frequencies to cater for your business case. And one important thing about the 5G, in LTE, the band, your carrier bandwidth is 5, 10, 15, and 20. So it max out to 20 megahertz. But on 5G, if we're talking about frequency range 1, the bandwidth is 100 megahertz. And for the millimeter wave, we're talking about 400 megahertz. And I'll explain this later on. And you'll see how we derive to this. Okay, let's get down deep into some technical concepts here. When we talk about the RAN, there are 3 layers in OSI model. There is layer 1, which is the physical layer right here. It's PHY. And then we have layer 2. This is pure OSI layers, stack layers. Then we have the MAC, RLC, PDCP, and SDAP. These are L2 layers. Yeah, they're the data layer. So the first one is the physical layer. Then on top of that, the data layer, and then layer 3 is the RRC, which is the IP layer. Okay, so this is just a concept that you need to know in order to go into the RAN splits. And now 5G has divided the RAN or split the RAN into 3 units. The lower band unit, it's called the RRU, it's called the radio unit, the RU. And then we have the DU, which is the distributed unit. And then we have the CU, which is the control unit. And some new interfaces just appear due to this, which is we have F1 interface, that's between DU and CU, and then F2 between this is where the CPRI and eCPRI, and also I'll cover that in a little bit. And then you have the E1, which is between the CP is the control plane, and UP is the user plane. So the control plane is where all the signaling go to, and the user plane where all the data. Also, this is an important concept that we'll cover. So this is how, and I'll explain why it's done like this later on. So 3 units when it comes to RAN: RU, DU, and CU. So let's dig deep into this. Look at this diagram. We have the radios right here, and then we have the DU right here, and then you have the CU right here, as we split RU, DU, and CU. So from the radio, from the RRH, which it stands for remote radio head, to the DU, you can either have the normal CPRI, or you can, I'm talking about this now, the connectivity here, or you can have the enhanced CPRI. This is for 5G. Because of the latency, you need to have a really high, these are fiber, high bandwidth when it comes to the front haul. This is called front haul. Front haul is the transmission between the remote radio head and the DU, which is, it could be BBU or CU or combined. So And then another front hole, it's called ROE, which is radio over Ethernet. This is the standard of 1914.3. So this is like an Ethernet connection between the radio heads and the BBU or the DU. So you got this, and then you go from the DU to the CU. You go through an F1 interface, and this is the mid hole. And F1 is totally new interface for 5G, and it's open interface. So through OPI, different vendors can communicate between the DU and the CU. And of course, the CU and the MEC. MEC is the mobile edge device, which is, since if you need low latency, why do you want to have all the computer and all the server that will do the computing in the cloud? You can have it close to the edge, closer where your customers are. And then from the CU, it goes to backhaul into the backhaul into the core network, right? And here are some latencies. If you want to know exactly the latency, 100, the air interface is 100 microsecond, and then between the within the front hole is going to be like 100 microsecond, and between DU and the CU it's 1.5 to 10 milliseconds. And the coverage, this is kind of also important. The CPRI or eCPRI, this is the distance between your radio head on top of the tower or on the building, all the way to the DU device. It's the front hole. It's between 1 to 20 kilometer. It's typically point to point. Then the mid hole, which is between the DU and the CU, it's called mid hole, and it's between 20 to 40 kilometers, point to point or point to multi-point. And then of course you have the back hole, which can go all the way up to 200 kilometers, and it could be point to point or all multi-point to multi-point. All right. So this is looking at the interfaces and the transmission between the radio and all the way to the core. So just to recap, so the radio unit has all the it has a digital front end. It is part of the physical layer. Actually, it splits the physical layer. So the physical layer, you have the low layer of the physical layer and a high layer of the physical layer. So that's why it's called, sometimes it's called lo-fi. So lo-fi means lower, the lower physical layer of L1. So all the baseband, the filters and the beamforming is right on this unit. Then you have the digital unit, which is it depends on the function split, which I'll explain later. You determine the actual function of it, and then you have the central unit. It controls more than one DU, right? So these are some important concepts for you to grasp. All right, there's something also important. It's called about the functional split. There's so many. There are like 8 different options where you split the radio part in order to achieve certain feature or accommodate a certain use cases. I'm gonna focus on the lo-fi split, which is option 7, which this is adopted, and option 2, which is at F1. If you remember, F1 is between the CU and the DU. So when you split the low layer, so you split the physical layer, the low part of the physical layer would be in the RU plus the RF. RF is is the radio frequency, which is part of the antenna active unit itself. So you'll have the radio right here as an RU, and then you have the DU and CU combined. So you split this into two, radio and DU and CU. So what is the DU and CU? DU and CU, they're the BBU, the baseband units. Yeah. So you can have the baseband unit, and it will have two functions. So split two is not going to be expensive, and it will be used. And one important feature of split two, the front haul will have significantly higher throughput. We're talking about 100 gigabits per second. So you will use it for millimeter wave. So when you want to use millimeter wave, the split needs to be option 7. All right. And also low latency at the same time, and the massive MIMO. So depending on the application, this is how you do the split. Split 2, it's going to be more expensive. Split 2, you will have the radio and the DU combined into one, and then the CU is going to be separated. So you will not have as much bandwidth, and this is typically used for macro cells, the sub-6 gigahertz frequencies and bands. So you ask me, okay, why are we doing this? What's the benefit? Okay, costs. This is be extremely cost effective, and you'll be able to control the load management. So you put functions where you want it, and then it is important for we're talking about cloud in virtualization. So you can virtualize anything except, of course, the radio part itself. It has to be local. So you can add function as you go on. So this is going to be extremely scalable and flexible. So this is one of the functions that were introduced in 5G and Open RAN technology also. This is, don't be scared also, this is the same way of the function split that I've shown you before, but here's the splits right here. And what I'm trying to show you at the bottom, where we can have also double splits. Double split, look at the last row. This is the split 7 and 2. So we split right here. This is 7, 2. And then we split at 2. You will have 3 pieces of hardware. The RU connected through front haul into the DU, which is the BBU. So you have the RRH, here is the remote head, and this is the BBU. And then you have the CU through mid haul. This is the mobile edge computing. It's just a server to do all the computations depending on your business case for low latency and high processing time. And then it will backhaul everything into the core. Okay. And this is where you see the split of the layers. You have the OSI layer 1 physical that I was talking about, and then OSI layer 2, which is the data link. Then you have the RRC, which is on the IP. This is another way to just stress the point. You can see here's the RRU, just to materialize it for you. This is the RRU, and this is the CU, DU, and these are the functions depending on the split. So split 2, a lot of functions will be in the RRU, and just one function will be in the CU/DU. Split 7, you will have only the lower part of physical layer, and everything else will be in the CU/DU combined. And as you can see here, the delays, the higher, split 7 will have less delay than split 2. and it will have higher throughput. So this will just give you an idea of how such a split will control latency and throughput. This is again the same splits, but here I'm showing that the cost and option 6 is for small cells, adopted by small cells Qualcomm platform. Option 7 is what we were talking about, and time to market is slower. Option 8 is already available. It's just, you know, you have everything in one small cell. So this is like a small cell right here without the splits, right? Okay, now we're done with the radio part. Let's see. Let's go into the core. You know, I'll try to explain it and simplify it right here. Before, you know, the APC, we used to have, you know, the APC components are the MME and the signaling gateway and the packet gateway, and then you have the home subscriber stage and the policy. Earlier on, there was no split between control planes and user planes. That would not cut it for us. So now they split into they split the planes into user plane and a control plane, and the split took effect in the signaling gateway and the packet gateway. You can see here, this is the control plane, and this is the user plane. User plane is where all the data passes through. This is the user constraint. This is like data. Here it's signaling, right? So how did it morph into 5G? Right. We have what's called. Let's start with access mobility management function, which is called AMF, and I'll shed a light on it on the next one. AMF took the MME into account. Then we have the session management function, which is the SMF, took part of the MME and the control planes for both the signaling gateway and the packet gateway. The user plane, this is the UPF, and it's just data. It's just like a data aggregator. It took the user plane functions of the signaling gateway and the packet gateway. Then we have the AUSF, which is the authentication server function, that you know, HSS from EPC functions are built in here. And then we have the policy control function, the PCF, took on the PCRF features. So this is how we morphed from 4G core, LTE core into 5G core. This is, I'll make it more, here, I'll put it more into perspective. This is user equipment. This is the RAN or even fixed wireless. These are the RAN part. And everything is dotted, is control. So now we have new interfaces. Instead of, you know, the interfaces are called N. In LTE, right here, they're S interfaces. Yeah, S1, S2. Now no more S's, it's N1. That's for the 5G technology. So, and what's interesting, your device, user equipment can directly communicate with the core, with the AMF, without even going through the radio part. This is N1. N2 is the interface between the RAN, the new RAN, and the core, the AMF. AMF, which we said account management, access management function. Then the N3, this is going into the user plane, which is data. So the data flows, you know, from the RAN into UPF through N3 interface, and then from UPF into the data network through N6. And UPF communicates with SMF through N4. So N1, N2, N3, N4, N6, and then all the above functions, this is called service-based architecture. So depending on the service, you get the connection. You get the signaling coming down from the service function blocks into the other function blocks right here through other interfaces, you know, denominated by like N, UDM, N, and EF. All right. So and here are the some of the acronyms right here, the explanation for them. But what you need to know that the RAN first entry into the core through AMF and UPF. AMF for signaling, UPF for data to channel it to the data network. So we talked about the AMF, which handles connection and mobility, and then the these are these AMF, SMF. Just because I'm covering these three, this is where the interface, you know, this is where RAN interfaces with the local. So AMF is for handles the connection and mobility. SMF, it will create the PDU sessions. It will decouple the control from the user claims, and also it performs the role of the DHCP server in the IP address management. UPF, think of it as a packet gateway. It just, you know, it aggregates all the data out of the core into the network, into the data network. This is another representation of you know, of the core. For instance, let's look at the fixed wireless access. You know, this is where you have your CPE at home. Then you communicate through the G node B. G, you know, it's for the 5G nodes. You know, E node B is for 4G. G node B is for 5G. And then, as if you remember, it goes through N2 into the AMF, and then this is N6 all the way. The data would come out, will be channeled out of here, right? All right. Now let's take it a little bit deeper to understand the throughputs in technology behind that. Now this is important. If you can just, the basics are important. You don't have to remember it right now, but try to understand it, because if you read it again, then you can, it'll make sense for you. Let's look at the carriers right here. We have this carrier, we have what's called SubCarrier Spacing, right? SubCarrier Spacing for the LTE, we have it at 15 kilohertz. This is the spacing between peak to peak of the subcarriers, right? So as we go down, the subcarriers are doubling. So from 15 to 30, so the bandwidth would really get bigger. So it becomes 100 megahertz in here. Double it again, the spacing, double it again, and it becomes in the thousands, and so on. All right. So the idea behind this is just to tell you that there are some concepts called subcarrier spacing that will determine the bandwidth of the carrier, right? And it's configurable. Then we have the frames. You know, the data is transmitted between your cell phone or your user equipment to the radio via frames. Each frame is 10 millisecond, and it has 10 subframes, right? So a subframe is 1 millisecond. So these are constants. I mean, you have to understand this. We have each frame consists of 10 subframes, and each subframe is 1 millisecond, making the frame length as 10 milliseconds. Let's go to this graph, and I'll explain what I mean here. Carrier spacing, remember, the carrier spacing will start with 15. So with a carrier spacing 15, we get only one time slot 0. Double it, 30 kilohertz, you get 2 slots. in a subframe. I'm talking about subframe. So the subframe is very dynamic here. This is one of the important feature of OFDM. OFDM, FDM is the frequency division multiplexing, and O is for the orthogonal. So that's the concept of signaling that 5G and LTE also based on. So 30 kilohertz of carrier spacing, you get 2 time slots in your subframe, and each time slots is 0.5 millisecond. This is the LTE right here. It's fixed at 0.5 milliseconds, by the way. You go to 60 kilohertz, it doubles again for 4 time slots, and the time slot lengths get smaller and smaller. Okay, as you go on, the subframes will be divided into more slots, and the time slot length is much smaller. Okay, these are some concepts. Now I'll explain how they map into the technology and into the 5G. We have what's called resource block, and if you it's the same when it comes from concept perspective as an LTE. What's the resource block? Each resource block right here, you can see this resource block. It's in pink. It occupies 12 subcarriers in frequency domain. It's exactly similar to the LTE, and one OFDM symbol in time domain. For LTE, the resource block in a TDD is only 1 time slot length, and it's 0.5 millisecond. But it's not the case in the 5G. It will vary. So this is a resource block. If you count the number of squares, there'll be 12, each one representing a subcarrier. And each subcarrier, if you remember from the previous slide, is 180 kilohertz. Yeah, that's an LTE. It starts there, but in 5G, it's not fixed. It depends on the subcarrier spacing. That's where the subcarrier spacing comes in picture right here. Resource element is just 1 square, so it's the smallest unit of resource grid. This is called the resource grid. This is a subframe. So the subframe consists of resource grid, and these are the resource blocks right here. So why I'm saying this? It's extremely important to know that we have a new term. It's called numerology, which it's indicated by the mu. And this numerology mu it goes from 0 to 4, and it's directly related to the subcarrier spacing. This is the spacing of the subcarriers. 15 kilohertz, 30, it doubles. And as it doubles, the bandwidth per RB per resource block gets also doubles. Because remember we said 12, so if you multiply 12 by 15, you will get that 180 kilohertz. That's for MU0. That's the resource band width. And this is the numerology. So this table, if you work into 5G, you probably memorize. Numerology 0, and this is with a subcarrier spacing, and you have the time domain here for the OMFD. So this is instead of 0.5 millisecond for LTE, it will be different. As the numerology gets bigger, the time duration for the time slot gets smaller and smaller. And this is how we accommodate actually the very low latency through these techniques. All right, so again, these are here the number of resource blocks, and this is the number of the bandwidth. So this is for you, this is important for you to remember. If you choose channel 15, spacing 15, your bandwidth can only get up to 50 megahertz. This is the bandwidth. LTE technology, we stop at 20, right? We cannot go more than 20 per carrier. Of course, if we aggregate carriers, we can, but I'm talking about one carrier. So if you, that's the number of our resource blocks that I was talking about in the previous slide. So if you do the math, you multiply 217 resource blocks by its width, you will get 8 megahertz of channel bandwidth. These are for the frequency range 1, so sub 6 gigahertz. You can always go up to 100. Yeah. If you choose this numerology 0, 1, 2, 3, 4. So for millimeter waves, if you choose numerology, we said 0, 1, 2, 3, then you can take it all the way up to 400 megahertz of a bandwidth for this for the channel that you're working with in the millimeter wave. So again, this is the bandwidth. This is very scalable. This is how you can control the bandwidth and hence the throughput. Okay, so this is just an example, just to put things into perspective for you. This is frequency band. For instance, if you look at let's say 41, band 41, which is the educational broadband.
Majdi, can you hear me?
Yes.
I just wanted to give you a warning. We got 4 minutes left. We have a couple of questions, and so we're just running short on time here. So just to give you a warning.
Oh, okay. All right. So yeah, for instance, band 41, you go, these are the bandwidth, and these are 15, 30, 60. These are the subcarrier frequencies that we were talking about. And so if you choose 30, you can go up all the way to channel 1 to bandwidth of 100. Okay. So now when you read these tables, you understand where it's coming from. And for the FR2, you can go to up to, for instance, 260. You can go, if you choose numerology 3, you can go to 400 megahertz of bandwidth. Well, we're running out of time, but with our 2 different deployments, whether it's called standalone or non-standalone. Standalone is where right here you don't have any LTE legacy core or radio, just it's like Dish Network. Dish Network is going standalone because they don't have any LTE network. But for the rest of the networks, if you already have LTE, you can introduce your RAN, the new RAN, and the LTE, legacy LTE will actually control that LAN. This is another way to deploy. So just, since we're running out of time, I just wanna let you know that we, at BuySells, we do have end-to-end demo systems that's on a standalone and non-standalone. It's all the way from, and we have it with some customers, all the way from the 5G radios to the core. And this is for non-standalone. And then we have our BBUs, which is the DU/CUDU, the concepts I talked about earlier on. We do have these equipments too ready. Then these are the radios. We have indoor radios. They're LTE and 5G. So they have both technologies. This is RRH, these are indoors, and antennas 66R. And of course, what's good about the radio, the new radio part, that you will go into 5G, and your bandwidth would go from 20 to 100 We also have the millimeter wave radios, 8x8 MIMOs. You can see the bands. We also have outdoor radios with massive MIMO technology, 16 by 16. Right here we have the AAU, which is antenna is included with the radio, so no need to have external antenna. And we're getting into the massive MIMO 64 by 64. And this is just a sample of, we're using this for RDOF. We already have RDOF products, and we're using this technology, the gamma and the BBU, and it will, go bypass the RDOF specification. This will cover the CBRS band and the 5G band, and it's 8x8 and it's 8x5 watts. It has the CPRI and eCPRI for 5G, and the split is 7:2, if you remember the split that I was talking about. And you can, here you can also, you have 5 carriers on the LTE and 1 carrier on the 5G band. Okay, these are also more of our baseband units and extension. We have extension cards to scale your network. Here we have the Gamma 632s, or it can be any indoor Gammas. It's so easy to install. It's like a Wi-Fi. Then you connect it to an extended unit. Each BBU can support up to 4 cells. Each cell can have up to 32 radio units. Extension units can be stacked. Everything is connected via fiber. Then you have the mid hole into the BBU, which backhaul it into the 5G core. So we have this 5G scalable and modular too. And we do support the heterogeneous network outside. So thank you. And these are the roadmaps that we're tracking. And now I can take questions.
Sure thing. Thanks, Majdi. Just to get through this real quickly, we do have a couple, like I said. So the first question is, I see beam forming. How fast is the handoff between each of the 5G cells?
Well, the handoff between 5G cells, it will be also, there is an X2 interface. So the X2 interface would remain like the LTE. I don't know the exact number, but it's according to the 3GPP specification. The handover should not be any problem between node, G node Bs, even between G node Bs and G node Bs, G node Bs and E node Bs, E node Bs and G node Bs, all according to the spec. The time, I can find it out for you, but you will find it in the specs. But through X2 interface.
All right. Another question is there unlicensed millimeter wave 5G spectrum in the US as we have in Japan? Citing 28 gigahertz is not auction-based, but it's application-based.
Yes, we have what's called the Turbo Plus, which will aggregate the CBRS, LTE CBRS channels with the unlicensed 5 gigahertz band. So that will act as millimeter wave hotspots, because speeds will go into gigabits per second. The throughput would go beyond the gigabits when you use that technology. And we do have it currently, and we're testing it here, even in the US, and it's called Turbo Plus.
Great, thanks, Majdi. That wraps up all the questions that I can see. And I know we did go a little bit over time here, so I'm gonna hand this off to Jamie to close us out.
Yeah, and also add one thing also here, Max. Thanks for this. As I mentioned, we have the RDOF products. The RDOF products, they're 5G. The radios are 5G, so you don't have to rip and replace the radios once you move into 5G. So they're already RDOF compliant and 5G ready.
All right, sounds good. Thank you, Marjorie. Thanks, Max, team at BuySells. Well, folks, that is it. Thank you very much for your time. I know it was very technical and in-depth,
Yes.
but hopefully that was a benefit to you, giving you greater insight into what 5G is all about. This webinar has been recorded, so keep an eye out. It will be published shortly. And if you have any questions at all, please reach out to Wave, MBSI Wave, Last Mile Gear, or the BuySells team. And we'll catch you on the next one. Take care, folks. Have a great day. Thank you.
Thank you very much.